Welcome back, everybody. It's been a little while. We're back from our hiatus. We're going to keep pushing on through chapter 8 of my notes, 8.16, deformation conditions. Here we go. Here's the setup. We've seen as far back as chapter 1 that it's often desirable to restrict the deformation problem to the deformations of row bar satisfying certain extra conditions, like fixed determinant, for example, or finite flat or whatever. Fix n, pi, and lambda as usual. So pi is a profinite group and lambda is a coefficient algebra. Consider the category f sub n, which is really dependent on lambda and pi, whose objects are pairs AV, consisting of an Artinian coefficient lambda algebra A, and a free A module V of rank n endowed with an A-linear continuous pi action. What are the morphisms in this category? A map from AV to A1 V1 is a pair of morphisms A to A1 of Artinian coefficient lambda algebras, and another map V to V1 of A modules, which induces an isomorphism on A modules from V tensor A1 over A to V1, and which is compatible with the pi action via the obvious commuting square. Okay, so here are the three major conditions that we need to be aware of if we want to have hope of representing a restricted deformation problem. Consider the following three conditions on a full subcategory dfn inside Fn. For any morphism AV to A1 V1 in Fn, if AV is an object of dfn, then so is A1 V1. So dfn is like closed under images, or I like to think about this as like being closed under quotients or something. Okay, so the second condition is let A, B, and C be Artinian coefficient lambda algebras that create a diagram like this. So we have a map alpha from A to C and a map beta from B to C. Consider an object A cross B over C V in Fn, and let V sub A and V sub B denote the tensor products of V with respect to the natural projections 1 cross beta and alpha cross 1 from A cross B over C to A and B respectively. Okay, so we're kind of taking the usual tensor products here. Then A cross B over C with V is an object of dfn if and only if both AVA and BVB are also objects of dfn. Okay, so dfn should sort of be closed under products essentially. I like to think of this as it's like closed under intersections. Okay, for any morphism AV to A1 V1 in Fn, if A1 Vn is an object of dfn and A to A1 is injective, then AV is also an object of dfn. I like to think of this as saying that dfn is closed under subobjects. So like quotients, intersections, and subobjects. And we'll look at these three conditions again next chapter, and we'll see them in a different light. Okay, so deformation conditions. Let's fix lambda pi in a continuous residual representation rho bar from pi to gln of k. Denote by V bar the n-dimensional K vector space K to the n with the K linear pi action given by rho bar. So it's the representation space here. A deformation condition D for rho bar is a full subcategory dfn in Fn, satisfying the three conditions above, and which contains KV bar as an object. I mean, we certainly want this to live there, right? Okay, so suppose we have a deformation condition dfn inside Fn. For a coefficient lambda algebra A and a homomorphism rho from pi to gln of A lifting rho bar, let V of rho denote the free A module A to the n with the pi action given by rho. So it's the representation space of rho. If AV rho is in dfn, we're going to say that rho is type D. It's a type D deformation of rho bar. And its strict equivalence class is a type rho bar D deformation. Define a subfunctor D sub rho, like cal D sub rho inside D sub rho from C lambda A to sets as follows. For any Artinian A augmented coefficient lambda algebra B, so for anything here, and any element C in D rho B representing a strict equivalence class of liftings rho 1 relative to rho to B, C is in cal D sub rho of B inside D sub rho of B if and only if rho 1 is type D. So it's like the type D deformation problem inside the main deformation problem, in other words. Extend the functor cal D sub rho to C hat lambda of A by continuity. That is, if B is any A augmented coefficient lambda algebra, let cal D sub rho of B and D sub rho of B denote the subset inverse limit over n of cal D sub rho of B sub n inside inverse limit over n of D sub rho of B sub n, where B sub n, they're the Artinian quotients of B. Okay. So proposition 19. If cal D is a deformation condition for rho bar, and rho from pi to GLN of A is a lifting of rho bar to A, then cal d sub rho inside d sub rho is relatively representable. Thank God, right? We can actually represent this thing with the universal coefficient ring. Okay, and this actually follows easily really from just conditions 1 and 2 on cal d, not even all 3. Corollary, if cal d is a deformation condition for rho bar, then cal d sub rho bar as a functor on C lambda satisfies HI for I equals 1, 2, 3 from Schlesinger's theorem, so it has a pro-representable hull. If rho is a lifting of rho bar, then cal d sub rho is nearly representable. Perfect. If rho bar is absolutely irreducible, then cal d sub rho bar is pro-representable by a quotient ring, actually, of the ring pro-representing d sub rho bar. All of this is like, oh, thank God, right? Like, thank God all this works correctly. Okay. And this is really just definitions along with the section, the information found in the section on Schlesinger's theorem, the main results of the subsection on relative representability, and then proposition 11 from a previous video. Okay, let's bring back the content of the previous video into the picture, the tangent module, the cohomological interpretation of tangent modules. Fix a type cal d lifting rho bar of rho of rho bar to a coefficient lambda algebra A. By the corollary, cal d sub rho is nearly representable. So we can speak of the tangent A module to cal d sub rho, which is a sub A module of T sub rho, the tangent module to the full deformation problem. Okay. And so this has to be necessarily a finite type over A because T sub rho is, right? And so we'll denote this by T sub cal d of rho inside T rho. If rho bar is absolutely irreducible and R is its universal deformation ring for deformations to coefficient lambda algebras, and if R sub cal d is the quotient ring of R representing cal d, then we know from the subsection, the video on Kähler differentials, that we have a commutative diagram of A modules as follows. TD rho sits inside T rho, as we just discussed, but then remember, we have a cohomological interpretation, or like a Kähler differential interpretation of these tangent spaces. T rho is just A maps from the sheaf of differentials tensor A, or completed tensor product over R with A to A. So what sits inside here? Well, it should just be the A maps from that same sheaf of differentials tensor A to A, but now you're complete tensor producting over what? The type D universal deformation ring R sub D. Okay, so there's really nothing to check here. This is all just definitions. Okay. But now let's bring in the actual cohomological interpretation of the tangent spaces from the last video. So we'll quote proposition 15 from our previous video, which identifies as A modules T rho and H1 pi and AV for V equals V of rho, the representation space of rho. So this was kind of one of the main results of the previous video. So the sub A module T sub D rho of T rho is identified then with some sub A module of this H1 of pi and AV. We'll call that H1 sub D of pi and AV. And that gives me a commutative square TD rho inside T rho. TD rho is isomorphic to H1D pi and AV. T rho is isomorphic to H1 pi and AV. And so then we have to have an injection here as well. Okay. So what we're going to try to do over the next couple of videos is we're going to try to look at specific restricted deformation problems, so certain type D deformation problems. And we're going to try to figure out which submodule of H1 of pi and AV this H1 sub D actually is for that given set of restrictions on the deformation problem. And this is going to be crucial because if you combine this with the results of chapter 4, where we get a handle on computing the sizes of a lot of these cohomology groups, you start to be able to build a lot of the machinery you need to prove R equals T, which is what we'll do in later chapters. So I'll see you all then, and thanks for watching.